A rational function has a particular form, and it looks like this. F of x, which is your rational function, equals g of x over h of x, which are both functions. In fact, they're a special kind of function. They have to be polynomial functions. And the h of x function cannot be equal to 0. Otherwise, we have a problem. So, going off of this definition, let's see if we can figure out which of the following are rational functions. And we'll put together a little chart here. And in this chart, we'll list some functions and expressions. We'll see if they're functions in the second column. In the third column, we'll check and see if they're rational functions. And if they're not functions or rational functions, or if there's some other note for them, we'll put that in that other column. So the first one is x squared minus x, all divided by 2x minus 1. So you may look at this and try to check it against that definition that we said, which is it has to be a polynomial divided by another polynomial, and you'll look and say, okay, well, there's a polynomial. It's a degree 2 polynomial, x squared minus x, and here's another polynomial, and you may be tempted to say this is a function, but it actually isn't a function. It is an expression. And the reason that it's not a function is because we didn't say that it was equal to y or equal to f of x. It's just an algebraic expression. So this is not a function. It's not a rational function. It's just a rational expression because it's missing the f of x. So if I had done this, then yes, it would be both of these. Okay, it won't be so tricky for this one. This is y equals 3x minus 2 over x minus 5, and I have a degree 1 polynomial function on the top and a polynomial function on the bottom. So this is a function, and it is a rational function. If I just give you y equals 3x squared minus 10, this is a function, and a rational function would need a function on the bottom, but this kind of does have a function on the bottom. It's h of x is just maybe 1, and so technically this is a rational function. It's just a really boring kind of rational function. Let's move on to slightly trickier ones. What if I have root 2x squared minus 5 over x cubed minus 2x? Well, do I have a polynomial on the top? Well, a polynomial needs to have x squareds, then x's, then numbers, and this does. Some people will think that the square root will cause it to not be a polynomial, but the square root is only with the coefficient. So this is a function, and it is actually a rational function. But if that square root were to be influencing the x, then although this is a function, it wouldn't be a rational function, because root x minus 1 is not polynomial, whereas root 2 x squared minus 5 is polynomial. And you can see that the difference is that the square root is only with the coefficient, where the square root is now influencing the x. Okay. Let's take a look at a couple of other things that happen with rational functions quite often, and that is to do with an asymptote or asymptotic behavior. One of my favorite words in math. Let's define asymptote. An asymptote is a line, usually horizontal or vertical, that a graph gets very close to but never reaches. So let's specifically look at the vertical asymptotes first. Vertical asymptote goes up and down like this, and they occur only if your rational function f of x has h of x at some point equaling 0. Now I said by definition h of x can't be equal to 0. What I really meant by that is h of x can't always be equal to 0. What happens when it is equal to 0 on a particular function is that you get one of these things called the vertical asymptote. There's no actual value that you can assign when the denominator is equal to 0, so you get some sort of discontinuity technically for most of what we'll see, you'll find a solution to your vertical asymptote when h of x is equal to 0. So I'll state that. This will be is a solution for any, and it's really only any possible vertical asymptotes. And in a little bit we'll see when they aren't actually possible. So for example, if I have a function and it's a rational function 2x squared minus 5x all divided by x plus 7, then x plus 7 equaling 0, which is x equals negative 7, this is the vertical asymptote. That's really useful because when you're going to sketch your graph, you go find x is equal to negative 7, and you know that the graph is going to do some sort of asymptotic behavior near that point, which basically means it's either going to go up like this or down like this on each side as it approaches that value. Okay, next let's take a look at horizontal asymptotes. So horizontal asymptotes go along the same direction as a horizon, and they occur when x becomes really large or x becomes really large into the negatives. This is what we call end behavior, is where we're looking for horizontal asymptotes to occur. So an example of that is if you have y equals 1 over x and you graph this, when you look at the graph and you look to see what is it doing as x goes to positive infinity, you'll see that the line gets closer and closer and closer to y equals 0, to the x-axis, but it never actually reaches it. And over here the graph looks like this, and in this direction y also gets closer and closer and closer as x gets closer and closer to negative infinity. So it's going, x is going towards positive infinity here. It looks like an asymptote is occurring at y equals 0 as these values get closer to 0, and in this direction it looks like it's an asymptotic behavior towards y equals 0 as the values get larger and larger and larger into the negatives. A much more technical approach is to take a look at it this way. Given that you have a rational function, so again f of x is g of x over h of x, and the g of x is polynomial, and I'm going to write out this polynomial as a to the m. So there's some x to the m value, like x cubed, and this is the coefficient am. And then the next value, well, this will go down by 1 if they're in degree order, and so I'll just keep these numbers the same so we know which coefficient is attached to which degree, and you just keep doing that until you get down to the last few. So x to the power of 1, and this would be the constant term at the very end. And on the bottom I'm just going to do the same thing, but I'm going to use the letter b instead. So b1 and b0, and so this is x, and I'll use an n instead because it could be different degrees to these things all the way along. This would be x and to the 1, and x to the 0, which is 1, which gives a constant term at the end. So if you have this, and I guess technically there's a little bit of a restriction, a to the m won't be 0, b to the n won't be 0, otherwise you wouldn't have those first terms there. So if you have this, then there's really three possible options, and those are option 1. If your m value is bigger or smaller than your n value. So you've got some function, and it looks maybe like, I don't know, x. So m has to be smaller than n. X squared over x cubed. And you can add whatever other things you want to this. You're really just looking at that first term, the largest term, or the degree of the top and the degree of the bottom. If that occurs and the top is smaller than the bottom for the degree, which is what my statement is saying here, then the line y equals 0 is the horizontal asymptote every single time. Option 2 is if the degrees are the same, what happens? Well, now we're dealing with an option where we've got a rational function and it's maybe x cubed and some x squared. And this is also x cubed and some stuff. And don't forget we've got some a value and some b value in front of here. We did with these ones as well. There's some coefficients in front of these things. And in the case where m is less than n, the coefficients didn't matter. But it turns out that in the case where m, the degree of the top, and n, the degree of the bottom, are the same, then we get a horizontal asymptote that we need the values for the coefficients before those degree terms, the highest degree terms. So if m equals n, then the line y equals, and now you need those terms. So a, and then the biggest value would be m. In this case, it's 3. And b, and the biggest value is n. In this case, 3. And notice m equals n. Right? We already stated that. Then that is the line. That's the horizontal asymptote. So if you had something like y equals 3x minus 2 over 2x minus 1, you can say, oh, they have the same degree, so m is equal to n, and that means the horizontal asymptote will be these coefficients divided by each other, just like that, which is a flat line at 1.5 or 3 over 2. And the last option is if m is bigger than n. What if the top is larger than the bottom? Well, then there's actually no horizontal asymptote. However, there could be some sort of other asymptote, and you can use long division to calculate those slants, or sometimes they're called oblique asymptotes. So let's take a look at some examples of how we go about finding all of the asymptotes.